Hey, thanks for tuning in. This is Frank Garcia, joined by George Lupret and Andre Devoli. We will be giving a presentation on an analysis of a rotating shaft on a VTOL to forward flight drone for machine element design taught by Dr. Justin Wilkerson at UTSA. The topic we will be addressing today consists of vertical takeoff and landing drones as well as fixed wing drones. We will be implementing traits of both body types in a concept design to develop a hybrid UAV. Now let me give a little background on the two types of drones I previously mentioned. The first is VTOL. VTOL stands for vertical takeoff and landing. These drones are generally used for short-range flights because of their ability to hover. They generally last between 20 to 30 minutes on a lithium polymer battery and are optimal for photography and surveying small areas of land. On the other hand, fixed-wing drones excel in forward flight. They are extremely efficient because of their aerodynamic properties. This makes them last extremely long in the air, which consists of 16-hour flights. This makes them extremely optimal for data collection and inspection of long-distance infrastructure. These drones are often less seen in public because of their cumbersome takeoff and landing operations. In other words, they need a runway or a slingshot in order to become airborne. This makes them less practical for everyday consumer use. By integrating these two traditional bodies, we optimize an existing concept design. This means that our hybrid UAV has the convenience and practicality of a VTOL drone combined with the aerodynamic efficiency of a fixed-wing drone, allowing longer missions. Because of this combination of features, it has the ability to carry a larger payload and withstand more rigorous weather conditions. Furthermore, our rotating shaft design offers high-performance steering and control in the air. I will now hand it off to George to talk about the purpose and the concept design we chose.
Hey guys, this is George. So I'm going to give you an overview of the purpose of our project as well as the concept design that we chose. The main purpose of our project was to optimize a rotating shaft mechanism that we initially designed ourselves for the concept drone. It's important to emphasize the constraints that we kept in mind while doing the initial design of the concept mechanism as well as the redesign. Some of these constraints include the drone's life, the aesthetics of the drone, as well as the cost of the project and the manufacturability. In the picture shown, you can see the concept design that we chose. It's commonly referred to as a manta ray drone. The pictures all represent a different phase of the drone's flight. In the upper left picture, you can see the drone in its vertical takeoff and landing position, and the bottom left picture represents the drone's forward flight position. Now I'll show you guys a quick video of how the drone works in motion. Now that you've seen the drone in motion, I'll pass it over to Andre so that he can talk about the mechanics behind the design.
Hey guys, this is Andre, and we're now going to dive into the actual design that we created for this drone that actually enables it to transition from forward flight to vertical flight and vice versa through this shaft mechanism. As any design requires, one of the first steps we did was to figure out which materials we were going to use in this mechanism. Since this project was so open-ended, we decided to use a ABS plastic forearm mount to connect our acrylic medium-high impact plastic shaft to a 90-degree rotating servo. The wing material was lightweight balsa wood, and the fasteners we decided to use were 8 1023 carbon steel screws to fasten everything together. To analyze the practicality of this original design, it was necessary for the group to run a few analyses using SolidWorks to analyze the stress and strain concentration factors, as well as the displacement and factor of safety when a constant force was applied to the front of the wing. It is important to notice that our minimum factor of safety fell below 1, meaning that the mechanism did indeed fail when subject to this load. It can also be seen that where the mechanism failed was the ABS mount connecting the shaft to the servo. This slide shows the same four types of data acquired. However, instead of applying the load to the front of the wing, we applied the load to the side of the wing. It can also be seen again that the factor of safety fell below 1, meaning that our mechanism did fail again, and you can see it failed at the same spot. Although in this analysis a slightly lower force is applied, it can be seen that the stress concentration factors in the mechanism as a whole is much lower due to the fact that this is a state of compression as opposed to the previous impact. As opposed to the two previous slides shown, which were static impact forces, this slide shows two different types of fatigue analysis ran when landing and when transitioning from VTOL to forward flight. Assuming a constant landing velocity, a force was calculated to determine the impact load taken by the mechanism every time the drone landed. With this force, we decided to run hundreds of thousands of cycles to see which point failed and at how many cycles it failed. A similar method was used in the rotational fatigue analysis cycle, in which an applied torque from the motor was used to calculate the maximum number of cycles the shaft could handle. It can be seen that the limiting factor in this design was due to the number of landing cycles capable of the mechanism, as it was only able to handle 100 landing cycles, whereas the rotational cycles had a minimum failure of 46,390 cycles. After gathering all this information from the original design, it became the group's objective to improve the overall mechanism design, to improve structural strength by reducing stress and strains, to extend its fatigue life, to reduce cost, and to improve manufacturability by either changing material or reducing material, or a combination of the two. I will now hand it back to George to discuss the exact improvements we made and to discuss the analysis from the second simulation.
So the first thing I'm going to go over with you guys is the new components and the components that remain the same for our new redesigned shaft mechanism. The first thing we need to look at is the rotating servo. We kept the servo the same in order to have a consistent power source throughout the project. The next thing I want to talk about is the brass gear that was added. This replaced the original 4-armed plastic servo mount that had 8 screws and a mounting face. This provided us with better torque transmission and a load distribution from the servo to the shaft. We also added a new component to the list, a 6061 T4 aluminum joint. This allowed the gear to be connected to the shaft. The original shaft, which was made out of a plastic material, changed to a 6061 T6 aluminum pipe. The original diameter that we had was 30 millimeters. The pipe itself had a nominal diameter of 15 millimeters. The last component added to the redesign was a ball bearing that was used to take axial and vibrational loads transmitted through the shaft. Finally, the material of the wing remained the same to maintain consistent force distributions in our simulations. As we previously mentioned, each simulation performed on the first design was recreated for the redesigned concept of the system. This allowed the team to verify whether the system's performance increased, and if so, what portions of the design it increased in. As you can see in the top left figure, the wing's end experienced a maximum displacement of 2.93 millimeters. This was a significant difference seen from the original's design displacement of 132 millimeters. This yielded a more rigid wing and enhanced aerodynamic properties of the drone. In the top right figure, we saw a significant increase in the factors of safety. The minimum factor of safety obtained would remain well above 1, meaning that the mechanism would not fail due to the frontal impact on the wing. The bottom two pictures show the concentrations of stress and strain in the mechanism. It can be seen that the maximum stresses and strains were found inside of the ball bearing, and only reached a maximum of 154 megapascals. For the second simulation, we analyzed the drone's wing with an impact coming from the side. We had a maximum displacement of 0.31 millimeters. The simulation yielded the factor of safety of 40, meaning that the shaft mechanism would not fail in case of this impact. In the bottom right picture, one can see how the maximum stresses are located on the outside of the bearing. As seen in the simulations of the initial design, this is due to the fact that the stresses acting on the shaft's end are compressive stresses. Moving on to the fatigue analysis performed, you can see in both pictures that the landing cycles and transition cycles had minimum effect on the life of the mechanism. As seen in the original design of the mechanism, it was only able to handle 100 landing cycles. However, the redesign allowed the mechanism to withstand 33,000 cycles. meaning that the shelf life of the mechanism would increase significantly. By analyzing the simulations performed, we can verify that the mechanism can withstand 50,000 rotational cycles. The following video shows the speed at which a common rotational cycle would occur. The table seen in this slide discusses the most significant data that was acquired from each static and fatigue simulation. This directly compares the maximum stresses, strains, and number of cycles for a complete understanding of the improvements that were made. From the data in the table, a 148% decrease was calculated for the maximum stress in the forward impact simulations. As for the side impact simulations, there was a 191% reduction in maximum stresses. Aside from the possible error encountered in the rotational fatigue analysis, the results showed a significant increase in the shaft and mechanism performance of the drone. The second to last section of this project consisted of performing a cost analysis on the original design and redesign of the mechanism. This cost analysis took into account manufactured parts and purchased parts for both the original design and the redesign. The total savings per assembly due to the redesign totaled out to be $23.47. Now, I'm going to hand this video back over to Frankie. He's going to tell you about the sustainability changes that occurred throughout the redesigning process.
In today's world, it is common for companies to be put under environmental restrictions. Because of this, we decided to take into consideration the sustainability of our manufacturing processes. As you can see from the pie charts on the left of their respective figures, our redesigned shaft mechanism had a substantially lower carbon footprint. Similarly, as seen on the pie charts on the right of their respective figures, the manufacturing process of the redesigned shaft consumed much less total energy. Now I'm going to hand it over to Andre to talk about the conclusion of our report.
All right, thanks, Frankie. In conclusion, this project was carried out with the intention of improving the design of a rotating shaft assembly on a vertical takeoff and landing to forward flight drone in order to increase its ability to bear loads while simultaneously increasing its usability. After extensive research and simulation, it has been concluded that the original shaft mechanism design was not only more expensive, but also structurally weaker than the redesigned model. This was primarily due to the geometry and material used in the rotating shaft, as well as the coupling system connected to the servo motor. By changing the material of the shaft from acrylic to 6061 T6 aluminum, implementing a brass gear, and adding an alloy steel bearing, the team was able to design a shaft assembly with improved load-bearing capabilities and an increased shelf life for greater overall performance. As technology advances and drones become a larger market of interest to working engineers and consumers alike, drone research such as this will continue to emerge as an important subject of interest with a vast range of potential improvements for a more efficient and advanced future. We'd like to thank you for taking time out of your day to watch this presentation, and we hope that you enjoyed it as much as we enjoyed producing it. As engineers, we constantly question the world around us and ask how things function, how they did in the past, and how they will change in the future. We hope this presentation piqued your interest in drone and aircraft development and made you question how these are going to change in the future for a more efficient and more technologically advanced means of navigating the skies. This project involving VTOL to forward flight drones is just one of many examples in ways that engineers are changing aircraft design for a better future. To further increase your interest in the subject, here's a short video over an Osprey aircraft utilized by the U.S. military. We hope you enjoy it. Thanks again, go runners, and God bless the United States of America.
Departure out of the HLZ, approximately 80 feet. We were most worried about the small arms threat. Probably about 80 feet, we started an aggressive left 180 turn.
To avoid another ambush, the team coordinated an alternate pickup site which took them once again through the narrow mountain valley pass, flying low and fast with zero visibility. Captain Thompson and his team successfully retrieved the assault team and headed back without further incident.
They brought 3 people off of the target that night, allowing for a lot of information. I believe this Taliban commander was directly related to IED facilitation in the area.
Back at Cannon Air Force Base, New Mexico, home of the 20th Special Operations Squadron, Captain Thompson reflects on the CV-22.
I think on this specific mission, we were aided by being in CV-22s versus another aircraft by the sheer speed that we do fly that final mile inbound to the HLZ. At a half a mile out, we were still 80, 90 knots, and we were able to keep that speed up until very short final. And with the use of the tilt rotors and pushing them all the way back, we can do a kind of a quick stop maneuver right on the target and then descend the aircraft from there. But the capabilities that it provides are really going to give dividends to our special operations community, especially 10, 15 years in the future from now.